Well, welcome everybody to the tutorial for the Automotive Virtual Prototype as part of the DVCon Europe this year. What we've done for today is we pulled together a tutorial on insights, learnings, items to look out for on automotive virtual prototypes. This is a joint presentation with Ingo Fellner from Bosch, Sascha Lloyds from Continental, Ralf Schleifer from the Car Software Organization, and Kevin Brandt from Synopsys and myself. So we'll take a tour through the supply chain and how things can work together and learnings. So we'll pass through and then we'll have at the end also some time left for questions on the presented material. Okay, then let me get started. Automotive virtual prototypes is the collaboration on making models available in various cases. And the virtual prototypes we're looking at from the OEM level, from the tier one level, as well as from the semiconductor level. The virtual prototypes are used slightly different as the development goes on. The key item we're going to focus today on is front loading. So we're looking at how can be things done things earlier, addressing the hardware software co-design. We're also looking at getting the software bring up early on the semiconductor side, on the ECU level, as well as on the OEM level, to gain time in the schedule. In order to have more time for continuous testing, integration, regressions, fault injection. So this is the main benefit and the main use case we're going to look at. Now, as we have a lot of different models around, so to speak, we thought it's probably good to give you an overview on which models we're really talking about here today in the tutorial, just to help and giving some guidance if there are people who are interested from deploying it newly. If we're starting on the top left, then is kind of the functional models which are on the concept phase at a very early stage. That's very often done in tools like MATLAB Simulink or Dataflow or just C++. But at that point, there is no real mapping yet to a particular hardware. The next level is then the host-based simulation. This is then very often done on Linux operating systems, which is done on the host, server machines, and functions are being developed with mockup GUIs and so on. But there is no specified or particular hardware mapped to it. As we go down, the timing is becoming more and more important. But also as timing gets introduced, we're seeing a decrease in speed. The next level we're looking at is the virtual hardware from an SoC level, as well as from the ECU level. So we're looking at here today primarily along these three angles. The items which we're not necessarily looking at is the RTL implementation from a speed perspective and also from an accuracy point of view. That's a very dedicated use case, which we normally see in the area of architectural exploration or benchmarking, but this is down to a very small number of users within the semiconductor companies in most cases. So the majority of virtual prototypes in automotive were moving along this angle here, what you see in the middle of this abstraction diagram. And we'll get back to this diagram over the time and refer to, so probably keep in mind this graph because we will have some reference to it. Now, one of the main challenges in the automotive virtual prototype deployment is the deep supply chain in automotive. In automotive, the full ECU software stack comes from various vendors. In many cases, the hardware abstraction layers are from the semiconductor vendors. There are different operating systems vendors or open source operating systems. The next level are then middleware layers. And what you see here on the right-hand side with the different color depiction is that each ECU has a very heterogeneous supply chain from a software perspective. So there is semiconductor vendor software, there is commercial operating system or communication stack vendors, there is functional software, there is tier one software, there is also OEM software in various forms. Some of them are delivered in source, they be ported in source, some of them are integrated in binary only because of IP protection and as well on reliability. What does it mean in terms of automotive virtual prototype? The cooperation is very essential between the different development partners because of the deep supply chain. The development should start very early and also take into account for those elements which are, for example, not modeled or there are certain abstractions. There needs to be the preparation for special builds and also the testing needs to be done along the supply chain. So ideally, the software development and the software suppliers are all using the virtual prototype as part of their development flow. In order to do that, that means it means a very tight integration from a project planning, from a commercial setup, as well as from a release process. So we'll get into that one a bit further in the next slides from the semiconductor vendor side point of view. So in NXP, the model development is an incremental flow. So as we have specifications available and the IP gets defined, decided, or third-party IP is getting integrated, we do an incremental release process. So we'll have an initial release and the focus and the content is then aligned specifically with the software releases. So here we talk about incremental flows, different cores, different accelerators, they get all integrated. The virtual prototype we're talking about here, we talk about system C loosely timed. That's primarily for gaining the speed. Items which we're not addressing here is the possibility of benchmarking. Although you can do certain amount of software statistics, obviously, like code coverage or instruction count. So you can get some insight, but the timing which you're seeing is not what you see later on hardware on purpose, because otherwise you would not get the speed, as it's called a so-called functional virtual prototype. As we do the incremental releases, what's a normal deployment is that you have the early adopters. Those are most the technical leads or the foundation software which is being put together in order to deploy it. And as the release becomes more rich, the more participants from the software community, from a testing, from a regression get added. That means also along that chain, respectively, the support for the virtual prototype needs to be planned and respectively scaled. The incremental flow is then also something which, as we talk here pre-silicon and try to gain a maximum in terms of shift left perspective, is that this release process is closely aligned from a content, from an abstraction point of view, with the subsequent recipients, if it's a software company, if it's a tier one, or if it's an OEM, that there is also a good common understanding what's in the model, what's not in the model, what's the abstraction being chosen, and the next question is then also how does it interact with the environment. So one of the items which need to be carefully looked at is that when deploying a virtual prototype in an intercompany setup is that the software regression is being integrated into an existing flow. In most cases, we're not starting on a blank sheet of paper. There are existing software flows and they differ significantly between the different user groups, from a driver, hardware abstraction, from an operating system, or from a functional model, from a functional software function development. The key in order to gain productivity and also to preserve the investment of the existing regression suites is that a virtual prototype is capable of fitting into existing regressions. And that is something which needs to be done and pipe cleaned even before the models do become available. So a close engagement on a project preparation is necessary. We have seen automations which are utilizing debugger scripting. We have seen regressions that use serial interfaces as they use equivalent serial interfaces to put the software test regression into an ECU at a later stage. So the virtual prototype need to support those interfaces in order to fit into an existing flow, because those test harnesses which are being used and deployed in the pre-silicon phase obviously will need to be reused downstream when hardware is available. So in many cases, some specific regressions which are used in the virtual prototype might not necessarily be ideally applicable in that setup. And that is something which is, as I said, very carefully taken to go through in the project preparation, and those technical setups, which interfaces are necessary, need to be done. And that's also the case for multiple software vendors, because here we talk about operating systems, we're talking about MCALs, and they all use separate setups. So a very robust tooling and scripting interface and very heterogeneous interfaces are necessary, because also automotive is a very heterogeneous application. There is not just one automotive. There is control code, there is vision, there is users interface driven applications, and those need to be taken care of. So this integration is very crucial for the success on the deployment on the virtual prototype. At this point, I would like to hand over to Ingo Feldner from Bosch to give into more insight into the deployment of the use cases. Ingo?
Thank you, Manfred. Yeah. Can you hear me? Seems
Yep.
so. Yeah, I will elaborate a little bit more on the application and challenges we see from a Bosch point of view by using virtual prototypes. Can you just click once, Manfred? I still see the old one. Now it works. So application and challenges of virtual prototypes. And as you can see from the picture on the left, we are engaged with virtual prototypes indicated by the bluish color as a tier 1 and as a tier 2. So tier 2 means we are delivering IP and models into that virtual prototyping game, and we are also consuming these models and building platforms of SoCs and ECUs for use in our different software use cases. When looking at the development phases where we employ virtual prototypes today, so we are employing them throughout the development flow from concept phase and very early design phases down to the post-silicon phase where hardware is already available. The focus in these early phases, and the engagement model that is depicted here engages us very early in the development flow, are mostly on doing feasibility studies, support internal decision making, and verifying concepts, let's say, before we enter into the implementation phase where a hardware specification is available, so we know in principle what to do. Then we take these virtual prototypes and bring up our software, bring up OSs, bring up the tooling, do all the things you can do before the hardware is really available, which is quite a lot. And in that phase, we may already be engaged with an OEM who has different requirements on using a virtual prototype. So these must then be mapped or provided then maybe also in different ways before we go into the post-silicon phase, where mostly quality and verification integration steps delivering to our customers is relevant. And as you can see, the timescales are quite different. So in that engagement model, we have quite some time for bringing up the virtual prototype, deploying it internally, and then preparing it for delivery. So in another engagement model, click please. We are engaged with virtual prototypes at a much later stage. So for third-party software development, an OEM may already be engaged with a certain tier 1 who has selected a tier 2, has selected a certain SoC for development. And we are now engaged with a virtual prototype to start software development on that virtual prototype. So the time or the delay for taking that virtual prototype into our organization and deploying it internally to a lot of customers all over the world is really important in that stage. And you can lose a lot of time if your environment does not fit or your regression setup does not fit into what comes from the OEM. So the use cases are very heterogeneous, and we must align these use cases in order to be fast in these phases and deliver to the customer. Click, please. Next slide. So what we have, thank you. As we have learned a lot from these use cases, and as we have seen a lot of different semi-environments, so the vanilla world that Manfred showed before from one semi that looks pretty good, looks a little bit different from our end, because we see that the virtual development methodology is not commonly established at suppliers today, which mainly manifests in heterogeneous setups and missing IP models, which are the main deficiencies at the moment, in my opinion. The heterogeneous setups are, on the one hand, on the technological side, which means you have to cope with all the environments, you have to cope with the different debugger tool connections. Everything must be set up in order to match the requirements of your internal developers, which may be very heterogeneous. But alongside with these more technological parts, there's even a bigger part on the organizational side. So the picture on the left shows the classical, let's say, design flow from spec over hardware to software. And now when you are attaching a VP to that game, the VP team will need to have interactions with all the different design disciplines in that existing world. So they will ask questions, they will bug the developers, they will distract them from the work they have been doing before, and they need to have the right priority to interfere into that process to deliver a VP that really has a high quality for the customer that needs to bring it into their software development. And secondly, the missing IP models may totally destroy the virtual prototyping use case. So if you are using, or if you are missing a critical IP in your VP, then some use cases may not be possible at all. For instance, imagine you are missing a security module or something like that is not available, and you're doing your safety argumentation on that. As a safety module, I meant, then things might be totally impossible, and it's then not fitting anymore to your design process. So what we are aiming for, click please, when we demand a virtual prototype, we see that the methodology must become an integral part and must be a reliable part of the design process. And as you can see from the circle picture below, the VP is fitting very well into that whole game of the development, and the interactions and organizational parts are clear. And with that, we can also ensure that the correspondence to the hardware is ensured, and that there is a reasonable automation in place, as Manfred showed before, for deriving these virtual prototypes and also keeping them up to date. And that also ensures a timely delivery of virtual prototypes, which is crucial in these early design phases to be up to date and delivered to your software developers. Another thing we see is that the VP must be used inside on the supplier side in the same manner as on the consumer side. So it must be verified by the internal teams that are developing the VP, and the software teams inside the organization must also verify that, because the knowledge is much deeper inside these organizations, and the testing should be reused in order to gain quality of the VP. And lastly, the adequate organizational representation. So the priority of the VP team must be there in order to ask questions, to get answers, timely answers, and also, again, to provide a high quality virtual prototype. So our future perfect click is we want to set on virtual prototypes like we did in the past, also in the future. But we see that we can only rely on these virtual prototypes when we can rely on the variants that need to be delivered down the line in the later design phases, so in the post-silicon phase. And the steps I mentioned before, if they are implemented, then we can rely on a defined quality, resulting in an improved time to market at really a lower risk and a lower cost. Otherwise, we burn, let's say, the advantages we gained before, we burn in delays and manual work. Which brings me to the last slide, click, where we map the technological and organizational challenges against the different design phases in the design process. So from concept to the testing phase, you are faced with a lot of technological challenges. You will need to adapt the VP to the different use cases. There will certainly not only be one model you have to build inside that design process. So reflecting that inside an organization is a pretty difficult step already to do. So once you master that, there are also the organizational challenges, which thank you, which are also very important and can totally hinder the use of a virtual prototype, or at least reduce the value of the virtual prototype. In the concept phase, these are the setup may not be available, so you may not even have chosen a certain hardware for your design. So you need to play around with different IPs from different vendors, and you may not have an awarding process that has taken place. And of course, the vendors are interested to protect their IP, but you want to look into the IP in order to assess KPIs to derive if a certain hardware fits to your algorithm or to your problem. So you need a very close collaboration, and it's a phase that is very, let's say, the least established at the moment, because it relies on bilateral setup, and these cost a lot of time, which reduce the effective use of virtual prototype in this phase a lot. The other two phases are, let's say, more established. We have a lot of VPs out there. We have done a lot of designs, but still we are lacking some essential parts of the methodology. For instance, that the VP is built against the specification, and we do not know the relation to the hardware. That goes back to the thing that Manfred mentioned before, that you must have the regressions in place. You need to reuse the unit testings from the hardware in order to build confidence that the VP is really showing real world things, and you're not encountering late errors or late surprises. Then availability of models is a key aspect in these phases, because the software people normally reuse the whole software stack. So you do not want to have certain setups or special setups for each and every VP. You just want to deploy a regression as it is today for the whole software stack, let's say. And if you need to connect to the outside world, so building an ECU or connecting your own models to it, you need to rely on a certain kind of standard in order to bring these different models together and make them interoperable. Of course, you can write wrappers, but that's typically costly, and that's also error prone if you are not relying on a certain methodology and standard for bringing these things together. So to sum up, click please, last click please. What we see for scaling the technology from point solution to common use is that we require these items I just highlighted to get a reliable setup, and we need a broad adoption in order to rely on the availability of virtual prototypes. And in order to bring them into larger setups with different semis, we have to have common practices to be applied when I want to use a virtual prototype in my setup or in my design process. Okay, with that, I want to hand over to Sasha, who is telling you more about the use cases of virtual prototypes.
Yeah, in my part of the talk, I'm here focusing a bit on software levels that shall be implemented and how they reflect in the requirements for a virtual platform. We typically see three different areas of where software might be delivered. We could have software on bare metal that is really directly accessing the individual bits and pieces of a microcontroller. We can have, especially in automotive domain, systems that are built on the AUTOSAR operating system. And today, more and more software, even in the automotive domain, is moving on some Linux-based operating systems. Click, please. We at Continental, we have a bit more than 20 years of experience in developing and applying virtual prototypes. And our aim is always to run the same software image that we later want to run on the real hardware, also on our virtual prototypes. And initially, when we started that 20 years ago, of these software levels that you can see here, only the bare metal application-based software was available. And at that level, coming up with a virtual prototype can be quite difficult because at this level, you don't have a clearly defined interface between your software developers and the people that are coming up with a virtual prototype. And this in the end means that really everything needs to be modeled in a very accurate way, which means you come up with a model that needs to be bit and probably even cycle accurate, being then at a very low simulation speed. And in the end, it turned out that this is causing a lot of iterations because the virtual prototype is being developed while also the chip is developed. And at that level, it's quite difficult to get something running. So for us, then the breakthrough for virtual prototypes came with AUTOSAR, where with the MCAL layers, you have a clearly defined abstraction level that you can use to communicate between software developers and the providers of the virtual platform, so that can talk which of these MCALs are using in which stage of your development, how are they used, and by doing that, you can come to a good roadmap, as Manfred has shown at the beginning, how your virtual prototype needs to be developed, how it needs to be extended over time to have there a good development flow. And also from the cycle approximately here, you can relax a bit and don't need to be that hard as for bare metal applications. Then with use cases growing and growing, today we are getting into the Linux domain. At the beginning, this was something that for me, as someone coming from the hardware level, also quite difficult to grasp. Use cases are growing, getting wider. Does it fit together with the simulation speed of a virtual platform? But in the end, we were sometime beginning of this year pretty much forced to try it out on a much larger scale than initially planned, as everyone had to stay in home office, didn't have access to boards. And so we said, okay, we do have this capability here. Let's try it out, whether people can work with it. And it worked out quite seamlessly. And the reason in the end fits out very well, because with the Linux server kernel, you have a still better level of abstraction that you can choose, and therefore do require less accuracy and can use even faster simulations here. So that here this worked very well. Next, please.
You should see the next slide. Should be up.
Yes, okay. Yeah, now I can see it. Yeah, so how to achieve your target? Start at a high abstraction level. So choose the targeted operating system and start with that one. And don't try to start with something that is bare metal and then see how you can reach the target on reaching your OS to run on the system. And start in a very, very early phase to align with the users on the virtual platform on what are their requirements, which simulation speed they will need, and what is their timing requirements in terms of do they have something that is real-time critical, and especially when it moves then from the tier 2 to tier 1, you will get at some point into a situation where you need not only the controller itself, but also other components of the ECU that need to be part of the model. And you need to be know very early what are the requirements there in order to get the system running. Something that is on our side working very well here is, for example, a watchdog running between the microcontroller and another ASIC on the ECU. That is a very nice use case for a virtual platform, because you can debug that even far better in the virtual platform than on real silicon. But it also here puts a lot of requirements into the area to get it running, because the watchdog has some real-time requirements, not hard, but they are there, that the watchdog needs to be served in a regular manner. And you need to be able to communicate between the MCU and the mixed signal IC. In our case, fortunately, the mixed signal IC is owned by us, so that we can see what communication interface the virtual platform on the microcontroller side offers, and try to adjust the mixed signal chip to that. But even that is already sometimes challenging. And if you would have two devices from two different vendors providing two different tool chains for virtual platforms, then this can be something that is getting very difficult. So with that in mind, keep talking to the users and refine the platform as needed. And very important, even if you have some real-time requirement, as I just mentioned with a watchdog, stay approximate in timing, so that you can achieve a good simulation speed and a good performance. With that, I hand over to Ralph.
Yeah, hello everybody. I hope that you can hear me. I'm representing the OEM end of the deep supply chain. You might not have heard about the car software organization. This is an organization within the Volkswagen Group dealing with hardware and software development for the entire Volkswagen Group. And I'm going to show you a couple of examples of real-life virtual prototypes on the scale that we have seen in the beginning of the presentation. I'd like to start with the host-based simulation, so the more abstract thing. If you are about to develop a multimedia application for an in-vehicle infotainment system, you're probably not interested in cycle accuracy, cycle approximate. Even you don't need to really run the target binary in the end. You can get along with a cross-compiled version of your application with all the business logic and the communication included, but still it is a cross-compiled version. And you can see at the picture on the left side of the slide is a laptop with a touch display, which we use for developing such high-level applications, allowing us to interact with the application via a touch interface. Other things where you probably don't want to go for a classical virtual platform, but where you would like to go for a host-based simulation are use cases like connecting Android Auto or Apple CarPlay to your to the infotainment system that you're developing. And last but not least, navigation certainly is something where you need to have real-time performance, where you would like to interact with the application. So we use virtual host-based simulation for that one as well. Why don't we develop that on the hardware, on the real hardware? Because it has a lot of dependencies, it has instabilities, a lot of disadvantages that you can get rid of if you abstract the lower layers of the system away and just focus on the development of the application. So this is the host-based simulation part we are working with. Coming to the right part of the slide, the virtual platform. We heard a lot about the possibilities, the advantages earlier, and I'd like to give you, again, real-life examples here. It's an in-vehicle infotainment system still, but it needs to not only have high-level applications running on it, but it also needs to implement power management and simple things like if the temperature of the unit becomes too high, then the fan needs to start and cool the system. And what you typically do is to put the stuff into a climate chamber, change the temperature, and see if the unit behaves as it should. This is costly. This is something that you cannot integrate into a continuous integration and testing process. So what we did, and what works really nicely, is to use the virtual platform to stimulate the AD converter interface of the virtual platform with a value that represents a voltage, which in turn represents a temperature, and then see whether the software running inside the virtual platform behaves correctly. If it turns on the fan, if it sets the fan speed to the right value. An interesting or a nice story is that you might travel to Scandinavia for doing winter testing with your car, and you have your infotainment system along with you in the car, and you never saw temperatures below 0 at that stage of testing. And then you recognize that the variable that you use to represent the temperature has been selected to be an unsigned value, which in turn leads to the fact that your infotainment system doesn't even start if you are up in Finland, in Sweden or elsewhere. So testing that in a virtual domain, I think, is a good thing and helps. Another very neat feature that we found, given that the security subsystem that was mentioned earlier is modeled fully in the virtual platform, is to also test certain security features. Assume that you have a multi-stage boot procedure. Each of the boot binaries is signed in your image, and each of the boot stages checks whether the next image is consistent and is not compromised by anything in between. Then you can do that nicely on the virtual platform because it's easy to manipulate the images that you would like to test. And it becomes even more interesting if the security mechanisms on the real hardware would lead to a bricked unit in case you have a successful test. Successful here means you prove that your boot procedure stops when you have a compromised part of any of the boot images. So with a virtual platform, you can, in the sense of error injection, try over and over again and test that over and over again without the risk of losing hardware samples, which is a realistic case in that context. The last example I'd like to mention here is to test power management. Now, this is not power management in the sense of a within SoC power management, voltage and frequency scaling type of power management. It's rather the type of the driver opens the door, then the infotainment system needs to wake up already in order to be available when the driver in the car selects an application, whatever he does. So you would like to use the time after you got the first signal that somebody is entering the car for bringing up the system. In the virtual platform, you can do that without having all the peripherals at hand by stimulating the software at the right interfaces, which you can access because you do a kind of a gray box testing and not a black box testing anymore. So these are examples where we benefit from the virtual platform. And as you see, we try to find the right sweet spot from a simulation speed perspective for the application we intend to develop and test. The next slide, please. I talked about the in-vehicle infotainment, one of the pretty complex ECUs within a car, but there are a couple of other ECUs that you need to have in place for testing as soon as you are testing functional chains which span over multiple ECUs. So the picture here on the right side is just a symbolic representation of how such an architecture typically looks like. You have the in-vehicle infotainment system, which drives a series of displays. It is connected to a gateway or other, might have another name for that one as well. And the gateway, again, is connected to various smaller other ECUs for dealing with the charging, for dealing with the seat position, with the climate control, with the automatic parking, just to name a few. And last but not least, also the back end. Now, if you are about to develop and test functions like function on demand, for example, you all of a sudden need to have the backend as part of your test setup. You need to somehow replicate the gateway feature in this picture here in order to be able to test the software that you intend to test in the IVI system. This is what we find one of the really difficult issues here. You cannot just simply pick one ECU, have either a host-based simulation or virtual platform for it and believe that you can test everything that runs on that one. You need to make sure early on that you get the simulation models on what abstraction level ever for the complete functional chains you're about to test. And this is with the deep supply chain we heard a couple of times. A real challenge to get things together, to get models and simulations talk to each other to be able to really develop and test these complex scenarios. But we managed to some extent and we benefit from it. With that, I'd like to hand over to Kevin.
Okay, thanks very much, Ralph. So yeah, I'd like to just return to a slide that you saw earlier in the presentation. And I'd like to present on the synopsis, automotive, the virtual prototyping technologies. So again, in this slide, this is where we see the OEM, the tier one, the semiconductor in their domains and their needs for different use cases for simulation. So from the lower levels required by the semi, and it really reaches up into the sort of multi-ECU simulation requirements just mentioned by Ralph there in his final slide at the OEM. So of course, the point here is really just to show the use cases at the different tiers, both at pre and post silicon. So with this, we can now show really how the Synopsys virtual prototyping tools as they apply to that supply chain simulation requirements. So next slide, please. So firstly, at the system and architectural concept level, what we have here is SaberRD. SaberRD is capable of model-based design. You saw this with reference to an earlier slide on abstraction. This would be sort of the high-level abstracted system-level models for doing sort of concept case studies, etc. But actually, the SaberRD's got quite a wide set of use cases. And these span from fast abstract modeling, as I just mentioned, for system requirements analysis, but also you can also model in high fidelity for use cases of, say, electrical efficiency, optimization, transient analysis, and that's through the technique of detailed electrical simulation. So analog simulation as well. So you're spanning quite a number of use cases there. But it fits generally with the many use cases of the OEM and the tier one. So at the semi and tier one level, architectural and performance studies, of course, are very important. That was kind of mentioned earlier by Ingo. And really, you're doing early studies of compute hardware, and these can be executed with a tool called Platform Architect. And Platform Architect can be used to evaluate KPIs, key performance indicators in hardware, and allow you to do very early trade-offs, say at the semi level, as well as looking into things like hardware, software, co-design, etc., and basically targeted at the tier one and semiconductor. Next slide, please. So looking more into the software domain, which has been a focus mostly of this presentation, starting with the middle block. So the middle block here of the virtual hardware simulation. So this is the Synopsys virtualizer and the VDK. These are basically VDK or virtualizer development kit models. Virtualizer provides the virtual hardware ECU simulations, and they're capable of running compiled software binaries. So we're talking about executing binary code built as if it were for the hardware. So there's no abstraction there. And it's running typically on ISS, instruction set simulators, with a full suite of peripheral models using System C, which has been referenced before. But this does allow for full software stack verification and provides a platform for integration and system test. with binary software images. So since it's a hardware model specifically for software execution, it spans the semi-tier 1 and OEM, as you see in the diagram here. And since it's a hardware model simulator, it's also ideally suited for hardware-dependent software development. So, of course, it's agnostic to software. The cases are not solely limited to hardware development software because you're running binaries at the end of the day. But of course, abstraction comes into the picture. As Ralph made clear, you wouldn't run a full navigation stack on something that was, modeling the bits of registers and peripherals. So while we're talking about that, if you move up the abstraction tree a little, more targeted towards the OEM, so at the right-hand side, you can see that block with Silver and TestWeaver in it. So Silver's a fast software simulator that executes production ECU application software compiled for the host PC. So it is a host-based simulation. With reference to AutoZAR, for example, it replaces the hardware-dependent MCAL layers, and it replaces that with a fast instrumented software implementation. So we're not simulating the lower hardware layers here. Of course, connectivity is still available here to do things like multi-ECUs, which would be like bringing different pieces of application software together. And it uses standards-based connectivity. Things like FMI, etc., and that's specifically there to support connectivity with third-party tools that may, of course, be in the design flow already. TestWeaver that you see here is a kind of separate tool linked to Silver, and it provides intelligent test automation for large coverage and regression. So typically used at the OEM. So again, tier 1 and OEM use cases covered by Silver and TestWeaver. Okay, yeah, next slide, please. Oh, sorry, just hang on a second. Well, no, next slide, sorry, yeah, go on to the next slide, sorry, man. So let's talk a little bit, so I just want to talk some about how Synopsys actually delivers and uses virtual prototyping through the supply chain. You saw quite a number of slides and you've heard about the supply chain. So what we do is really provide a platform for virtual prototyping. And this really includes models, modeling tools, system debugging analysis tools, as well as integration with a wide range of flows in the automotive supply chain. So it's these technologies that that serve the ecosystem. So looking at this, we can see things like hybrid calibration and measurement, fault injection, which was already mentioned. The architecture design, again, has really been covered there. But of course, it's all about simulation, connectivity, and ecosystem support. Okay. Next slide, please. Okay. So for semiconductor, Synopsys, we have this initiative called the Center of Excellence, and we engage with at the semiconductor level. And this enables us to sort of share modeling efforts of a virtual MCU or SoC. So the deployment of the virtual prototype for semiconductor software development and enablement of the automotive tier 1s, this has got to be done through a sort of collaborative process of deployment. Manfred also talked about the incremental development, and certainly as the hardware is developing, we're sort of developing the virtual prototype hand in hand with the semi. So for tier 1 and OEM, of course, they are the customers of the semi. Generally, we're delivering virtual ECUs or multiple SoC or ECU designs, and it sort of acts with this Center of Excellence. It sort of acts as a system integrator in collaboration with the tier 1. So again, Ingo talked a lot about lots of things coming together, lots of things having to play together. Again, we're kind of engaged at that level as well and supporting that level of integration. And this, of course, enables the deployment of a process from software development to system integration and test, and through to the verification team. Okay, next slide. So really, finally, Synopsys has a proven track record. We've been doing this engagement with semis for some years now. We're also, of course, engaged with tier ones and OEMs in deploying virtual prototyping environments. So it's not really all about tools. Even though I'm talking about tools here, it's not really all about tools. It's also supporting that supply chain. It's about supporting it with efforts and technology to facilitate these simulations. And we've seen significant growth in this over the past number of years. Deployment and enablement expertise is actually key to facilitating this. And what I would probably call it is a sort of cross-tier model delivery ecosystem. How's that? So that concludes the presentation from the Synopsys virtual prototyping side. So let me summarize. Next slide, please. So I'd like to summarize on behalf of all my co-speakers today. So some of the key, and so in summary, I just want to summarize some of the points that we heard here from all of our sessions. So some of the key and common aspects out this tutorial is really about shifting left. You heard shifting left, and this drives new requirements into the development flow from a planning and a supply chain interaction perspective. And it's also important that virtual prototypes are available with different abstractions in order to match the use case. It's not one size fits all. So in order to cope with the ongoing development of virtual prototypes, concurrently with the use cases, they're incrementally developed. So again, they're done in the pre-silicon phases and also need to fit seamlessly into into integration and regression flows. As part of that, use cases have to have early and continuous alignment in the supply chain. So another key aspect is that all software supply chain partners need to support the use of virtual prototypes. You heard Ingo talking about this as well. And really everyone has to support it for their part of the software stack. There's multiple players in a software stack through the tiers, but it's key to getting them all on board and engaging them all with the virtual prototypes in order to make the virtual prototyping project successful. So from an enablement perspective, virtual prototyping tools, they must be able to provide a continuum through the supply chain of use cases and facilitate close collaboration in model creation. We have to build models together that will talk to each other efficiently. So from a tooling perspective, that really has to be as flexible and open as possible. And just at the bottom here that you'll see a link there. I also like to highlight that the tutorial content is also addressed in detail in the Arbeitskreis Automotive, the virtual prototype platform, and it's available via the EDA Centrum link at the bottom there. So with that, thank you. I'd like to thank, well, take the opportunity to thank all of the speakers today, Manfred Tanner, Ingo Feldner, Shasa Leutz, and Ralf Schleifer. I'll close this part of the presentation now, and I'll open up for questions.
Okay. Thanks, Kevin, for wrapping up. Any questions? I saw in the chat window, there was one question, if virtual prototypes was used in throughout COVID. And I think, yeah, Ingo, you already answered that one, that unavailability of boards help is something which a virtual prototype can overcome. One of the experience I made, and what I'd like to add that one as well, is specifically when first silicon is out, it's a very demanded piece of hardware. That makes it very difficult to scale with the number of users who would want to run some software on it. So that is where a virtual prototype can help. We also have seen with various countries that sometimes hardware is spending quite a bit of time in customs. So that's something where virtual prototype also can overcome availability and enable software development, because it just scales across the different platforms. Obviously, export control and legal legislation need to be maintained and adhered to, specifically when it gets to encryption and security, as that becomes more and more used and deployed in the virtual prototype side. Any other question? there was the question about the white paper. White paper was also probably comment on that one real quick. Quite a few more people contributed to the white paper, so you just can download it there. And if there are any follow-up questions, then there can be also the offers can be reached.
There's another nice one with the biggest blockers.
Yeah. I would say the minds of the people using it, or getting the mind to be able to accept using it. People are used to boards and want to have them on the table to touch them, and don't trust the virtual platform. That's, I think, the biggest blocker that I see, at least for the beginning.
For me, it's still organizational representation. I highlighted that before. So it's for me a very heterogeneous setup, and I cannot rely on anything. That's the main issue I'm facing. And I think we are dealing today with virtual prototypes a lot like it is hardware, and we are attaching it to hardware development departments, which is, in my opinion, wrong, because it's essentially software development, and we need to learn a lot more from the software field here in order to deploy virtual prototypes in later design phases also.
And to add to that, the higher up you come into the supply chain, into the stack from semiconductor vendor to the OEM, the more complex it becomes to get the supply chain coordinated, to get all the bits and pieces that need to run on the VP really running on the VP. This is really a challenge today.
Yeah, I see also two items which need to be addressed. And that's, I would say, also probably an invite or a recommendation to join the System C Evolution Day. A lot of also has to do with common interfaces for different protocols. So common practices or standards. There are standards out there, but they are not covering all the needs which are needed from a deployment point of view within the SoC, but also between SoC and ECU levels. So common practices or de facto standards is something which probably is helping the deployment. That's one item. The other item, one of we've experienced on when it gets to deployment, a virtual prototype means that a software organization or a software vendor needs to change their way of working. If they have an established work process and the people in the organization know what it means to develop software on a hardware, they have very often implicit requirements, like what I mentioned, the regression. Changing the platform from a development point of view normally creates a hump as part of the shift left, because the resources get deployed earlier. And the other item is you're asking the software developers to commit their work products on a different platform. And that is something which is also necessary to show and have a close interaction that they can commit their work products on a virtual platform, specifically in the pre-silicon phase. So part of it is the change management process to move to a different virtual platform. And overall, that's not an insignificant cost and risk, which the organization very often needs to assess. Can they shift the development platform in order to gain onto a virtual platform?
I'd like to pick up the last question from the chat from Joachim. Yes, verification is an important thing. There are certain areas, not in infotainment, but rather in the autonomous driving area, where you need to do a lot of verification and where you can simply not make all of this testing on real hardware in real cars. So you need to have means of doing that in the virtual domain. This is an important one. And also the scaling of verification is an area where the virtual platform is really helping, because you don't want to build up a dedicated test racks for each and every special use case. You would like to have a software-defined setup that you can instantiate, ideally, and that you can bring up in a cloud environment, run your tests on it, destroy the setup in the cloud environment, and use the underlying resources for yet another test scenario. So this is, on the OEM side, one of the clear goals, to become more virtual also in testing.
And maybe to add to that, so it's for us also always surprising how differently specifications can be interpreted. So the one who's building the model, although it's built against the specification, it, let's say, reveals another understanding of how the specification can be interpreted. And with that, you can find a lot of things very early in early design phases by using an executable artifact instead of something that is just written down and understood by different people differently. So that's of quite high value for us, as you were mentioning, return on invest. So if a certain feature doesn't work in the hardware, it can easily lead to not being applicable in the fields. That's what we saw, at least with virtual hardware in the past. That if we wouldn't have been using virtual hardware, that the device that we have built wouldn't have been working appropriately for our customers.
I would like to take the question of Jakob, as it fits quite well to what I had in my part of the talk, how important timing really is for a virtual platform. And I think one thing that I've shown is that with higher levels of abstraction, if you're moving away from the bare metal to AUTOSAR or Linux, the timing requirement is getting less, and that's fitting quite well to what you here wrote with hardware timing is assumed to be totally random if you are going into the Linux domain. So that is, of course, the case and simplifies aspect also for the virtual platforms. But on the other side, we do have use cases that are requiring a certain ASIL level, and that requires that faults are detected within a certain time. And you don't want to write two different softwares, one on the virtual platform and then later one that goes into real hardware. So you want to write one software that you can use later in the real hardware, and that also runs on your virtual prototype. And therefore, the timing is, with certain restrictions, of course, important, and needs to be respected, as otherwise some tests or security measures that the software needs to take in order to reach the ASIL level will fail on the virtual prototype.
Yeah, just to add to that a little bit, especially in the more hardware dependent software, as you say, and in the controller domain as well. Timing and AUTOSAR is all about timing. And they're in the likes of an XEV, electric vehicle kind of domain as well. Some of the timing requirements can be actually quite strict. You have very small task sizes for a lot of these deeply embedded controller mechanisms. So certainly very different from something at the application level. Yeah, I would kind of agree with Sasha that you need to get it right at the virtual prototype.
And maybe to add to the continuum point, so if you can employ hybrid or also emulators together with your virtual setup down the line, you can also push this at least, maybe not like you're doing with virtual prototypes, the scalability, you will use the scalability, but at least if you have integrated it very well with your emulator or hybrid prototyping setup, then you can also take these measures maybe for the hardware guys to assess that the timing is correct.
Okay, well, thanks everybody. I think there is no more questions or any additional questions. I see people are starting to drop off and join probably the next sessions on the DVCon. And let me just wrap it up. Thanks everybody first of all, for the co-authors to prepare. That was really good. I really appreciate it. Thanks for everybody dialing in. And I think there is also the possibility to download then the presentation later on from the DVCon site. So thanks everybody, and then also enjoy the rest of the virtual DVCon conference, also in the virtual meeting rooms. Probably we see you there. Thanks everybody, and enjoy the rest of the conference then.
Thank you, bye.
Okay. Thank
you, goodbye.
Thank you.
Bye.